Welcome to the lesson on number systems. Upon completion of this lesson, learners will be able to describe number systems and differentiate between different number systems such as base 10 and base 2 systems. Learners will also be able to mathematically convert between base 10 and base 2 systems and recognize the importance of binary systems in computer systems and robotics. Let's describe what a number system is and its importance in robotics and computing. A number system is a fundamental method for representing numerical values that computers and robots can process and understand. These systems are critical as they enable accurate representation of essential data like positions, speeds, and sensor readings, forming the foundation of how machines interpret and work with numerical information. Numbering systems are essentially the way we use a set of digits to describe any particular number. For example, if we take the number 100, there are different ways to represent it depending on the base of the numbering system. The most used system is the decimal system, which is a base 10 system. This is likely because humans have 10 fingers, making it natural to count in tens. The digits in the decimal system range from 0 to 9. When describing a number system or working with multiple number systems in the same document or context, we often use a subscript to indicate the base of the system. For instance, if we see the number 101101 with a subscript of 2, it tells us that the number is in binary. Subscripts can also represent other bases, such as 4, 8, 10, or any other number. However, the focus is usually on base 2, binary, and base 10 decimal. In computer systems, binary is the standard number system because it is straightforward to represent the two states, such as on and off for switches or high and low for voltages. These states correspond to 1 and 0, making binary an ideal system for digital systems and registers. These registers store information using highs and lows, essentially leveraging the simplicity of two distinct states, on-off or true-false. Other number systems, like octal or base 8 and hexadecimal or base 16, are often used because they are easy to convert from binary. The octal system includes digits 0 through 7, while the hexadecimal system uses digits 0 through 9 and letters A through F to represent values 10 through 15. Why is this important? Because base 2 conversions to octal or hexadecimal are efficient due to their relationships as powers of 2. For example, grouping 3 binary digits together gives one octal digit, and grouping 4 binary digits gives one hexadecimal digit. This makes these systems highly practical for computing and digital applications. Now, let's look at how to convert between different base systems. For example, the decimal number 5362 can be broken down using place values, where each digit is multiplied by a power of the base, 10 in decimal. The table shows a systematic approach. First, identify each digit, 5, 3, 6, 2. Then determine their place values, 10 to the power of 3, 10 to the power of 2, 10 to the power of 1, and 10 to the power of 0, which simplify to 1,000, 100, 10, and 1. Next, multiply each digit by its place value. 5 times 1,000 equals 5,000, 3 times 100 equals 300, 6 times 10 equals 60, and 2 times 1 equals 2. Finally, sum these products, 5,000 plus 300 plus 60 plus 2, to get 5,362 to the base 10. The subscript 10 means we are using base 10. This method works for all base systems. Just replace 10 with the appropriate base number. Moving on, let's understand the binary number system and how to convert binary to decimal. The binary system uses only 2 digits, 0 and 1, making it ideal for computer systems that operate using on-off electrical states. In this example, we're converting the binary number 1011 base 2 to decimal. The conversion follows a systematic process. First, identify each binary digit from left to right, 1, 0, 1, 1. Then, determine their place values using powers of 2. 2 to the power of 3 equals 8. 2 to the power of 2 equals 4, 2 to the power of 1 equals 2, and 2 to the power of 0 equals 1, as binary place values double each time moving left. Next, multiply each digit by its corresponding place value. 1 times 8 equals 8, 0 times 4 equals 0, 1 times 2 equals 2, and 1 times 1 equals 1. Finally, sum all products, 8 plus 0 plus 2 plus 1 to get 11 base 10 in decimal. Notice how the subscript 2 in 1011 base 2 indicates it's a binary number, while the result 11 base 10 shows it is in decimal form. Let's take a look at how to convert a decimal number to its binary equivalent through a step-by-step division method. To convert decimal number 45 base 10 to binary, repeatedly divide by 2 and track the remainders. Start by dividing 45 by 2, giving a quotient of 22 and remainder 1. Continue dividing each quotient by 2 until reaching 0. 22 divided by 2 gives 11 remainder 0, 11 divided by 2 gives 5 remainder 1, 5 divided by 2 gives 2 remainder 1, 2 divided by 2 gives 1 remainder 0, and finally 1 divided by 2 gives 0 remainder 1. Read the remainders from bottom to top, last to first, to form the binary number 101101 base 2. This same method applies to conversion to any base system by replacing 2 with the target base number. So now that we've done binary to decimal and decimal to binary, it's important to note that it's not always easy and convenient to carry out these multiple steps of dividing, keeping the remainder, and dividing again. Binary coded decimal, abbreviated as BCD, offers a simpler alternative to traditional binary conversion, especially for larger numbers. Let's use 5,362 to demonstrate this method. Instead of performing multiple division steps, BCD converts each decimal digit individually into a 4-bit binary number. In BCD conversion, 5 becomes 0101, 3 becomes 0011, 6 becomes 0110, and 2 becomes 0010. Each decimal digit must maintain a 4-bit format because the largest decimal digit 9 requires 4 bits 1001. The leading zeros are crucial and must be preserved. These 4-bit groups are then combined into a sequence, keeping the groups distinct with spaces and marked with a BCD subscript. Important note, the BCD result differs from direct binary conversion of the same number. For example, 5,362 would have different representations in BCD and pure binary. While these forms aren't interchangeable, BCD provides a faster conversion method when detailed calculations are not necessary. Let's understand why binary representation is essential in computer systems. When programmers write code using human-readable characters, variables, and commands, computers need a standardized way to interpret these elements. Each letter, number, or symbol must be translated into a format that the computer can process. This is where binary coding becomes important. It provides a universal system for converting human-readable programming language into machine-understandable instructions. American Standard Code for Information Interchange, or ASCII, provides a standardized way to represent text in computer systems using 7-bit binary codes. Notice how A is represented as 01000001, while the number 1 is 00110001 in this table. Every character, including letters both uppercase and lowercase, numbers, and special operators, has a unique binary representation. These pre-existing codes enable compilers to convert human-readable programming language into machine-executable binary instructions. The ASCII table shows how each character maps to its unique binary sequence, forming the foundation of text representation in digital systems. In summary, a number system provides a standardized method for representing numerical values that computers and robots can process. These systems enable transformation between decimal or base 10 and binary or base 2 numbers through specific conversion steps. The importance of these conversions becomes clear when we consider that computer CPUs operate using binary, that is, zeros and ones, to perform machine-level tasks, making number system understanding important for robotics and computer programming. Thank you.